Hey y'all, today we're going to look at titration curves of weak acids and weak bases when they're being titrated with a strong base or acid. We're going to look at specific points of the titration curves. We're going to look at the shapes of the titration curves, and we're also going to focus on how we can, just by looking at a curve, determine whether we are titrating a weak acid or a weak base. Let's go ahead and get started. The first thing to understand about titrating weak acids or weak bases is that the shapes of the curves are going to be different than when we are titrating strong acids and strong bases. And the reason for this is because of what that weak acid or weak base turns into. Remember, during a neutralization process, we create two things. We create water and the conjugate. In the case of strong acids and strong bases, the conjugate was negligible. In the cases of weak acids and weak bases, though, the conjugate is a weak acid or base itself, which means that we're going to change a little bit of what we're doing. Entire titration processes will be graphed on a curve just like they were with strong, but let's take a look at some very important and specific points on this curve to see how it differs from the strong titration we looked at last time. The first clear difference between a strong titration and today's weak strong titration is that a shoulder is formed on a titration curve of a weak acid or a weak base. Now, when I'm saying a shoulder, what I'm talking about is right at the beginning of the titration, there's a rapid change in pH, followed by a gradual change for a period of time. And then as we reach our equivalence point, it changes rapidly again. That shoulder that you see is a clear indicator that what we are titrating is a weak acid or a weak base. The second major difference between a weak strong titration and a strong titration is where the equivalence point is found. For a strong acid, strong base titration, because the conjugate is negligible, the pH at the equivalence point is neutral, 7. However, with a weak acid, strong base, or a weak base, strong acid, we are creating a weak conjugate of the original species. This means at the equivalence point, what we have present is actually the conjugate of what we started with. So if we started with a weak acid, at the equivalence point, we have none of that weak acid left. It has all turned into its conjugate base. That means at our equivalence point, we have water and conjugate base. And a base in water, we know, increases the pH, which means the pH at the equivalence point of a weak acid strong base titration is greater than 7 because of the presence of the conjugate base. One thing to remember here is that the strong base is gone as well. Just like the original acid is gone, the strong base has also fully neutralized. So we don't have any strong base left. We don't have any original weak acid left. All we have left at our equivalence point is the conjugate base and water. That's why the pH at the equivalence point is going to be greater than 7 when we are titrating a weak acid. If we flip this to a weak base being titrated, like in the graph on the right, what we see here is that at the equivalence point, the pH is less than 7. And the reason for that is because as we are titrating away that original weak base, it is turning into its conjugate weak acid. As it turns into a conjugate weak acid, remember the original strong acid that we're adding and the original weak base are gone. They're neutralized. They're out. And so at our equivalence point, all we have left is weak acid and water. And a weak acid and water, we know, will decrease the pH. So the pH at the equivalence point of a weak base strong acid titration is going to be less than 7 because of the presence of the conjugate acid. One more important point to understand in any neutralization of a weak acid or a weak base is halfway to your equivalence point. So for example, If it takes 20 milliliters of strong base to reach my equivalence point, halfway to that would be 10 milliliters of strong base added. If it takes 40 milliliters of strong base to reach my equivalence point, then my halfway to equivalence point would be at 20 milliliters of strong base added. The reason for this important point we'll talk about a little bit later, but it comes down to the fact that we have equal moles of weak acid and conjugate base, or weak base and conjugate acid present. When we set it up in an equilibrium expression, because remember, this is all equilibrium, those two terms will cancel. And when they cancel, what that tells us is that our Ka value is equal to our H plus concentration. Or in the case of a weak base, the Kb value is equal to the concentration of hydroxide, OH minus. So halfway to the equivalence point is very important, because if the H plus concentration and the Ka are equal, then the pH is equal to the pKa. And so this point in particular is critical when we're looking at weak acids and weak bases, because it is the central point of what we call our buffer zone. And we're going to talk a little bit more about buffers later. But because of the fact that buffers are so important in chemistry and in biology, we want to know where our weak acid, weak base system does the best job of buffering. And that is going to be where the pH is equal to the pKa of your original species of acid, or in the case of a weak base, the pOH is equal to the pKb. When it comes to these kinds of titrations and titration curves, there are a few things you're going to need to be able to do. The first thing is identify specific points on the curve. The second thing is draw the curve. And the third thing would be, if you're shown a curve, interpret it. So we're going to focus today on number one, identifying key points on the curve, and then number two, drawing the curve. We're going to do most of this on the whiteboard. So let's go ahead and get started with our first practice problem. Our first practice problem is going to be the titration of a weak acid, acetic acid, with a strong base, sodium hydroxide. We're going to look at 4 points on the curve. So let's go ahead and get started with the first point. This is before the titration has even begun. So what we're looking at is just a solution of only acetic acid. What I'm going to do is I'm going to draw the titration curve as we calculate each point. Now, I'm titrating a weak acid with a strong base, but before we start the titration curve, no strong base has been added at all. So let me explain how we're going to set up this first practice problem. I've got a few things already on the board here. You would be expected to write these yourself, so go ahead and take a second and do it. The first thing I have is a curve that is currently not filled in any way, shape, or form. On the x-axis, I have sodium hydroxide added. On the y-axis, I have pH. The second thing I have here is a simple rice table set up to show that this is not neutralization yet, okay? We're dealing with the first point before the titration has occurred. The final thing that I have set up here is the equilibrium expression. The Ka value for this specific process is 1.8 times 10 to the negative fifth. That's the Ka for acetic acid. So with this setup, I'm going to deal with the first part of the reaction before any neutralization has occurred. So what I'm basically saying is, what if there was just acetic acid in water? The position on the x-axis where this would be is at x equals 0. Okay, that's our origin. So what we're looking for here is the pH before I added any hydroxide. We are not neutralizing yet. In order to do this, I'm going to plug in my equilibrium values, treating it just like an x squared problem and solving for x. Now here's the thing. We're going to go ahead and initially ignore x at the bottom here, this minus x. We're going to ignore it just for a minute. If that X value is big, and by big, I mean bigger than 0.005, then we will need to revisit this because that's the 5% rule. But if it's less than that, we can continue to ignore it and we're just fine. So in this problem, X equals 0.00134 molar. Now, that value right there, 0.00134 molar, tells us that the concentration of my H plus is 0.00134, which is 1.34 times 10 to the negative 3, which means my pH is going to be somewhere between 2 and 3. Specifically, the pH of this at the beginning is 2.87. So my initial concentration of H plus, dealing with this like an X squared problem because we're before the titration has occurred, has led me to a concentration of H plus and a pH of our origin. Let's look at the second point now, halfway to the equivalence point. The second place on our titration curve that we're going to look for is the halfway to equivalence point. This is a very important place because it's the place where our amount of acetic acid has been cut in half, and thus the moles of acetic acid is equal to the moles of conjugate base. Let me explain how this works. What we're going to do is set up our Ka value, and I'm going to use moles here instead of molarity. Now, the reason I'm going to use moles here instead of molarity is because in our equilibrium expression, this unit right here, moles per liter, and this unit right here, moles per liter, they're in the same exact beaker, which means the volumes are the same. That means the volumes cancel. So what I can do is set these up with moles instead of molarity, and because the volumes are the same, we're all good. So what I'm going to do is I'm going to rewrite my equilibrium expression, but I'm going to do this in a little bit of a different way. All right, you'll see what I'm about to do. Okay, so if you look at this, what I'm doing is I'm basically doing a rice table, but I'm doing it within the formula itself, within the expression itself. So what I've got here is a situation where I've got the concentration of H plus times 0 plus the moles of base added. Why do I do that? Well, if we remember back to my equation here, my neutralization equation, for every 1 mole of the hydroxide that I add, I convert 1 mole of CH3COOH, my acid, into its conjugate base. So for every 1 mole of base that I add, I create 1 mole of conjugate base, right? My conjugate base. That means I have the same number of moles of conjugate base as the number of moles of base that I added. We're going to assume that we start with 0 moles of my conjugate base. In this problem, it's an important assumption. Second thing to understand is that every single mole of my strong base that I add removes 1 mole of my original weak acid. So what we have here is 2.5 times 10 to the negative third, which is the number of moles of my weak acid that I started with. And I'm going to subtract the number of moles of base that I added. Halfway to equivalence point means that I've added 1.25 times 10 to the negative third moles of base. So what I'm going to do is I'm going to plug that in now. So when I set up this problem, what I see here is that my Ka is equal to H plus, concentration of my H plus, times 1.25 times 10 to the negative third divided by 1.25 times 10 to the negative third. This means these two cancel. And therefore, my Ka is equal to my concentration of H plus. My Ka is 1.8 times 10 to the negative fifth. Therefore, my concentration of H plus is 1.8 times 10 to the negative fifth. And if my H plus concentration is 1.8 times 10 to the negative fifth, The pH is going to be somewhere between 4 and 5. Specifically, it's going to be 4.74. So what I'm going to do is I'm going to put that up here. Couple things to note. How many milliliters of my strong base did I add to get to this point? Okay, because that's the x-axis. How much of the sodium hydroxide did I add? So if you look, I added 12.5 milliliters of sodium hydroxide. Again, that's half of the acid that I've removed now. So I've added 12.5 milliliters of sodium hydroxide. Now let's take a look at what we're going to do at the equivalence point. All right, so that's the next point, which is 25 milliliters of sodium hydroxide added. The third point on the curve we're going to look at today is at the equivalence point. Now, at the equivalence point, all of my weak acid and strong base are now reacted away. They're gone because moles of acid that we started with and moles of strong base that we added are equal. That means what we have left is only weak base and water. The problem is, at our equivalence point, we can no longer use this Ka expression because we essentially have no moles of my weak acid left. Because of that, we can't have a 0 in the denominator. We need a transition, therefore, to using the Kb. So what I'm going to do is I'm going to write the equilibrium expression, assuming that we only have a weak base in water, right? Because a weak base in water is going to be dictated by the Kb equilibrium expression. Couple things to note. Number one, what we are dealing with here is almost identical to what we dealt with at our first point before we started the titration. We're going to go ahead and assume that we start with no weak acid and thus no OH minus. Okay. Now, this is a bit of a stretch, but here's the thing. We're going to assume this neutralization went to completion. And so essentially we're saying, all right, we're dealing with an x squared problem again. So with this x squared problem, I need the new concentration of my weak base. Now I know moles of weak base is going to be equal to moles of my original weak acid. So I know I've got 2.5 times 10 to the negative third moles of my weak base present because every 1 mole of my weak acid turned into 1 mole of my weak base. But here's the thing. The volume changed. I added 25 milliliters to the volume now. So I need to calculate the new concentration of this weak base. All right, in order to do so, what I'm going to do is take these number of moles and divide it by the new volume. That means the new concentration of my weak base is 0.05 moles per liter. I'm going to use that in the solve. Okay, so again, x squared problem, new concentration of conjugate base, finding now the concentration of hydroxide. Also, make sure that you're using the Kb. So obviously this is Ka. When I'm calculating the Ka to Kb conversion, remember we've already talked about this, Ka times Kb equals Kw. So if I take the Kw, 1 times 10 to the negative 14th, divide the Ka, 1.8 times 10 to the negative 5th, I get the Kb. With the x squared problem again, I'm going to set it up looking like this, where it's 0.05 minus x, but I'm going to not solve with the x initial. I'm just going to ignore that for the moment. Okay, when I ignore that for the moment, if I end up seeing the x values a little bit too big, I might need to go back and adjust, but right now we're going to ignore it for the ease of solving. In this situation, when I solve for x equals 5.3 times 10 to the negative 6. I need to understand that that's equal to the concentration of hydroxide. And I'm looking for pH. So I can do one of two things. I can convert this to H plus using 1 times 10 to the negative 14th, or I can convert this to POH, negative log of this, and then use 14 minus that to get to my pH. Either way, doesn't matter. I prefer to go from this to POH though. So the POH of this would be 5.27, which means the pH is going to be 8.73. That's what I'm going to put up there at the equivalence point, a pH of 8.73. Now, here's the thing. The first 3 points on the curve are arguably the most critical and the most likely that you're ever going to look for. What I'm now going to do is connect the dots. Okay? In order to connect the dots, I need to remember the shape of any weak acid, strong base titration, and that includes a shoulder. So I need to make sure I include the shoulder when I'm drawing and connecting these dots. I can't just draw straight lines. So what I'm going to do is I'm going to start with the shoulder, flatten it out right around that halfway to equivalence point, and then a steep rise to the equivalence point at 8.73. Now here's the thing. I found 3 points on this curve. We could find a fourth, somewhere beyond the equivalence point, but instead I'm just going to explain to you how to solve for it, and then we'll look at this in class. Beyond the equivalence point, at that position, we have excess strong base. So now it just becomes a question of how many moles of my strong base is excess and how many liters of that solution do we have. It's the same as any acid-base dilution, strong acid or strong base dilution. That's the same problem. It's just excess strong base. So we're not going to solve for it in this video. It's already a long enough video. But in order to solve for that, if you were to ask any point beyond the curve, you could do so. You would just have to know that you have excess strong base, and you'd be solving using that to find your pOH and then convert that to your pH. That wraps up today's video. Let's do a quick recap. We did a single problem in this video, but this problem of drawing a titration curve of a weak acid, strong base titration was pretty intensive. We had to be able to use 3 different points on the curve before playing a game of connect the dots. We needed to know the shapes of weak acid, strong base titration curves. We needed to know how to handle different positions on the curve. So today we looked at the 3 that are arguably most important. We dealt with before the titration began, where essentially it was an x squared problem. We dealt with halfway to the equivalence point, where we recognized that stoichiometrically every mole of weak acid that we started with would be reacted with 1 mole of my strong base. Halfway to the equivalence point, half of my weak acid was gone and was converted into my weak conjugate base. That meant in my equilibrium expression, those 2 values canceled, and my Ka was equal to my concentration of H+. We then looked at the equivalence point, where at the equivalence point, we had a transition to using my Kb expression because we had no weak acid remaining. And then beyond that, remember, you have to handle it like you would an excess strong base problem. And that's just a basic solution stoichiometry type problem. So nothing to really worry about, and we'll cover that directly in class when you get in here. Today's video was written, directed, produced, and edited by Ruby Codrington and Allison Wen. Thank you all for watching it. I hope you enjoyed it, and I'll see you in the next one.